Hello, Peter here. In the last episode we finished the point lights, and in this episode I'm going to try to do both steps that we need to do for the spotlights in one episode. The thing is that the spotlight is basically the same as the point light. All the things that we need to do are identical. The only thing is that the code is slightly different in the sense that it's not about point lights but spotlight types, and also that a spotlight has a cone, or actually two cones, the inner and the outer cone, and we need to do something with that. But instead of you having to watch me wire up all the code again, I'm just going to do them step by step ahead of showing them, and just show the differences. So the very first thing that we need to do is to adjust our material template, and I'm going to do that now, and there will be a jump cut and I will be back. So back after the jump cut, that is done. I also noticed that my capturing program OBS was still capturing the full screen from the gaming videos, but I made this look like it's my desktop now, so it takes the display capture option. Yeah, I've done it. Let's see what I've done real quick. It's completely the same as what we did before. In the template here, I just copied the point light 2 and renamed it to SL normal, SL color, called the material function and hooked it up, and added a new add node to add this to the rest. So this, as I told before, is just for copy pasting. It has no other function. And this is our real material for the sphere, the MSDL wood oak, and there I did the same thing. We add the SL normal, SL color parameters, call the function. Of course, we now hook up the diffuse texture, which is our oak wood texture. Have an extra add to add it all to the stuff we already had, and then connect it up to the emissive color. No mysteries here, it's exactly the same as what we did before. I'm only going to support one spotlight for this tutorial. You can add more, of course, but one is enough, I think, for a realistic situation. So that's it. We can keep this, and now we need to go to our blueprints. And the first thing we need to do is in the SDL level data actor, we need to now collect, just as we did here, an array of point lights. We need an array of spotlights, and we need to get the spotlights in the level. So I'm going to do that real quick, back in a second. Okay, I've done that, added the array of spotlights, and in the event begin play, just after where we set the array for the point lights, I just create the same code, get all actors of class for the spotlight, and then set the spotlights array. And then again, as the last one, we have to set the whole tick to false. So that's all we have to do in the level data actor. So let's compile this and save this and close. So now we can continue with the grunt of the work, which is in SDL component. Now this is our event graph, and we are in the SDL tick here. We are going to have something similar as what we see here. We only will have one block like this. We're going to do a get nearest spotlight, then set spotlight. And we need to do that only once after here. So let's do that, but we need to create those functions, and I need to create some variables and settings. So I'm just going to do the variables and the settings and the get nearest spotlight, and then I'm just going to show you, because they are very much the same as for the point lights. So jump cut. Okay, I'm well on my way coding the get nearest spotlight, and what I did is I added a new boolean lit3 for in the SDL tick. Theoretically that's not really needed if we only use one parameter in the material or set of parameters, but because I want to keep it slightly flexible, I'm just going to continue with what we have done here with lit1, lit2. I added 3 settings. The spotlight multiplier, which has the same kind of function as the point light multiplier. The spotlight radius correction is the same as point light radius correction, because even a spotlight has a radius. Basically that's the distance away from it. But then there is one other, and that's the spotlight angle correction. I also want to be able to, in our component, say that it should react slightly different to the light of the spotlight than the angle, the cone angles of the spotlight are defined as. And then I coded it up again. You have to basically do it all again because all the types are different. But the input is now spotlights. You have a new lights array, the one that we're going to remove the nearest from so that we can return it. We have a distances array. Then we iterate all the lights and calculate the squared vector length, the squared distance, because that is more optimal instead of doing the square root. Many times we only do it once there. From the distances array we then take the minimal one and remove that index from the new lights array. We also get it from the original one to return and do some calculations on. So the first thing is, of course, the square root we take as the distance, and we take the attenuation radius, apply the spotlight radius correction as a percentage, add that to it, and then check if the distance is within the attenuation radius of the spotlight. That will define if we are lit or not, or at least partly, because I said I was only on my way. We have to do something here to make sure that not only are we within the radius, we also need to be within the cone of a spotlight. So, and that I'm going to wire up now, and I'll get back to you to talk about it. Okay, let's have a look at what I've done right now. We already coded the check if we are within the attenuation radius by checking if the distance is less than or equal to the attenuation radius and the spotlight radius correction added to it percentually. But then we just went out to lit. I now created an end node because there is something else we need to check. And that is, we need to get from the spotlight component the outer cone angle, which is the outer border of where light is emitted. Then we had our spotlight angle correction, and in this case that will just be in degrees, so I just add it to it. And we need to check if we are inside that outer cone angle, corrected with the angle correction. And if the cone angle is greater or equal to the angle we have with the object, with the light, then we say, okay, then we are lit. And we will set the boolean there in the result. So how do we calculate that? Well, first we get the world rotation of our spotlight component, get the rotation x vector, which is the forward direction, normalize it, get our object's world location, and get the world location of the spotlight as well. Subtract world location of the spotlight from our object location, then normalize that too. Then we can do the dot product, and after the a cosine in degrees, we will have the degrees that we are having with the spotlight. And then we can see if that is within the cone angle. Now we're almost done with this, but you may have noticed that there was one more output here, and it's cone intensity. The spotlights in Unreal work in that way that within the inner cone you have maximum intensity. Okay, there is a fall off because of the radius, but the whole inner cone has the same intensity at the same distance from it. But when you get beyond the inner cone into the outer cone, there is a fall off. And I'm just going to not complicate this too much, I'm going to implement a linear fall off in the outer cone. But it does make it look a lot better. So that is the last step for this get nearest spotlight, and I will be back when I've done it. Okay, it isn't getting prettier unfortunately, but hey. From the spotlight component I now got the inner cone angle, because we need to have a linear fall off from where the inner cone stops to where the outer cone stops. I simply do that by subtracting the inner cone angle from the angle that we have, and I subtract the outer cone. I subtract the inner cone angle from the outer cone, which is then corrected as well by the angle correction. I divide these two and then do 1 minus that and clamp it to 0 and 1. So we get an intensity between 0 and 1, and it will be 1 exactly at the border of the inner cone angle, of the inner cone and the outer cone, and then linearly drop off to 0 where the outer cone ends. Now this kind of creates a bit of a problem. If we would set the inner cone and the outer cone to the same angles, then this one will become 0 and we have a division by 0. So we don't want that. So that is why we have a select here. And I also need to check if my corrected outer cone angle is larger than my inner cone. Greater than. If that is so, then we can safely pick that value. If not, we're just setting it to 1, because then the intensity would be the factor 1. This one is going to be a factor later on, a multiplier. And you have to see that in the backward direction. This code is executed because of the return node, so it works this way. The division by 0 is not going to happen if it turns out that the outer cone is equal or less, but that's even more stupid, to the inner cone. So this is completely safe. Now we have all the outputs here except the nearest light, which is nice to have as well. And that would be this one. This is the nearest one, and we have to hook that up there. So this completes our get nearest spotlight. Okay, now I will save this and I will do the set spotlight. See you in a while. So this is the set spotlight. As you can see, it looks almost identical to the set point light. The only major difference is cone intensity here. We also promote that one to a specific variable, a local variable. Otherwise it's the same. If both last lit and lit are false, we can safely return. Otherwise we go on, promote the variables. These are the parameter names. The type, of course, for the light is different. It's now a spotlight, so we can get the spotlight component. We even promote that one to a local variable. We have our trace. We have the same objects we are tracing for, so world static, world dynamic, and destructible. You can add if you want. The start for the trace is the position of our object. The end is the position of the spotlight. We say trace complex. We have a debug here. Then we subtract the location of the spotlight from our object position, normalize it, reverse the direction, because we removed that from our material function, if you remember, and that will be the normal. The result from the trace, if that is 0 and internal let is also true, then the internal lit will be true and we set it, or it will be false based on these on this Boolean operation. And from there we are starting to set our two parameter values, the color parameter value and the normal parameter value. But the color we need to calculate, it's the same as with the point light, the only difference being that we're using, of course, the spotlight component, and that we incorporate our internal cone intensity. So in this bit where we do the inverse squared rule, we now also multiply with this value that is between 0 and 1 for the fall off within the cone, so between the edge of the inner cone and the edge of the outer cone. This will result in a color at a certain intensity, which we set as the vector parameter value. And then we return if we are lit or not. So yeah, pretty much exactly the same as the point light, except for the cone intensity. Okay, so having done that, we now can go to our event graph and are already prepared the call as well. So first we get from the SDL level data our array of spotlights. I check if there are any in there. If not, we don't do anything at all, we don't need to. But if the length is greater than 0, we have a spotlight or more. So then we can call the get nearest spotlight here. And as you see, we should be able to do the same thing as what we did here with the point light, where we call it twice in a row. We have the same mechanism here with the out spotlights, but we're not using it right now because I only need one. That's why we also have the lit 3. Purely theoretical, we don't really need that one if we only do it once. So yeah, only difference again, this cone intensity, which we just hook up to cone intensity here, and then we set lit 3, and we give the right color parameter names to the set spotlight function. Now the only thing we need to do for this to work is to make sure that the settings for the spotlight, for how we react on spotlights, are actually editable, and also that the default values are correct. So in this case I would say this one should be 1. The correction ones can all be 0 for now. So let's compile this and save it, and now let's see what's happening. First, let's have a look at all our spotlights and see. Well, at least the ones that are on the wall. Well, my spotlights, of course. That should be these. Yeah, they're all there. And what they have an inner cone angle of 0. Let's make that one 20. And let's make the outer cone angle 60 so that we can see the fall off between the two. And that we can see that within the inner cone there is no fall off. So something like that. Right. Now we can take our ball, our sphere, and in SDL see if we now got our new settings. Yes, we have spotlight multiplier, spotlight radius, and correction. So that's all cool. Let's save that level, and okay, it wants to build the lighting. Well, it's not really needed for this test because we will see it anyway. So I press play. Now these lines are still from, now you see there is a line there. And you see it gets the light from that spotlight. Let's go a bit more to the, like that. And you see it, the fall off seems to work, yes, and there is an area where the intensity is the same all the time. And then it falls off. So yeah, this is successful. It works like it should. Awesome. Well, that's it for this episode, guys. I hope you liked it. And that, I think, is enough for the SDL component. There is one thing we're going to add to the SDL component, and that is the SDL light. I'm not really sure right now if that is where we start in the next episode on dynamic lighting, but it might well be so, that we create our own light. But anyway, I hope you like this one, and see you in the next episode. Bye bye! Hello, Peter here again. Just wanted to say thanks for watching this video. Please let me know what you thought of it in the comments. Below there are links to other episodes in the series, and don't forget to subscribe so you are the first to know when the next episode is up. Thanks again for watching, and see you in the next video. Bye!